Good morning all. This is Shubham from Clarkson University. I work with Dr. Sulapa Pitambran. So today I'll be talking about evaluation of chloride-induced corrosion in reinforced calcined clays and volcanic ashes based alkali-activated concretes. So to start with the problem, the recent surge in infrastructural growth has led to a high cement demand and cement production. Hence, that possesses a threat to sustainable development goals. Hence, we need to look for low environmental impact binders. Alkali-activated materials are one such category. So these materials are processed using a solid aluminosilicate powder mixed with a highly alkaline solution to produce a hardened binder matrix which has improved durability and mechanical characteristics. Traditionally, fly ash and GGBS or slag has been used to produce these alkali-activated materials, but with rapid decommissioning of thermal power plants and the competitive use of SCMs in concrete has led to challenge their availability for production of alkali-activated materials. Hence, this motivates us to look for other alternatives that are calcined clays and volcanic ashes, which are one such emerging category of alternatives. So let's look what are these calcined clays and volcanic ashes. Calcined clays are thermally activated low purity kaolinitic clays, whereas volcanic ashes or natural pozzolans are pulverized form of volcanic eruption products. So they are both rich in alumina and silica, that makes them a good geopolymer precursor. However, the mechanical and durability characteristics of calcined clays and volcanic ashes based alkali-activated concretes has not been yet investigated at far. So this study aims to investigate the chloride-induced corrosion in calcined clays and volcanic ashes based alkali-activated concretes through potentiodynamic testing, and also aims to examine the suitability of OPC standard specifications in case of alkali-activated concretes for predicting any corrosion activity in them. So for this study, we have used 3 different types of calcined clays and 3 volcanic ashes sourced from different parts of US with varying oxide compositions as shown in this table. Looking at the particle size, Va2 is the finest one and CC2 is the coarsest one. These 6 aluminosilicate powders are then activated using a hybrid solution of sodium silicate and sodium hydroxide. However, they are further blended with calcium hydroxide in case of CCs, and in VAs they are blended with CC2 and calcium hydroxide to enhance their engineering performance. Here you can see the activator parameters which are optimized for compressive strength. You can see solution to binder ratio varying from 0.6 to 0.9. These are the concrete mix proportions which are used for this study. It is to be noted that all these concrete mix proportions have produced a minimum compressive strength of 40 MPa by the end of 28 days, and we have used OPC with the water to cement ratio of 0.45 to benchmark the performance of our alkali-activated concretes. So the specimen preparation procedure is a bit peculiar in this case. We have used Lollipop specimens 2 inch by 4 inch size with a centrally located rebar. This rebar is prepared in a manner that only 60 mm length is exposed for chloride interactions and rest of it is sealed. So and this assembly, the Lollipop specimen, is cured for 28 days, ambient curing, and then it is exposed to 16.5% NaCl solution, and thereby the corrosion testing is conducted at designated intervals. However, to conduct corrosion testing, we need to have this 3 electrode setup where the rebar acts as a working electrode, silver by silver chloride electrode acts as a reference electrode. So this is a sample figure of our electrode setup, which is then connected to potentiostat to get all the readings. So we have used 3 different electrochemical techniques to get insight about the corrosion activity in alkali-activated concrete. First one is open circuit potential or the corrosion potential when there is no current flowing in the system. What is the potential there? This is one of the most widely used corrosion index. However, the ASTM limit for OPC based binder specifies that any OCP or open circuit potential above 250 millivolt would indicate that there is high chances of corrosion in that system. Second technique which we are using here is linear polarization resistance. So this is in short called as RP. RP is the slope of E versus I plot, which is obtained from forward scan from open circuit potential minus 30 millivolts to plus 30 millivolts at a scan rate of 0.1 millivolts per second. So this is a sample RP plot. Thirdly, the most critical parameter is corrosion current density. This is named as I-core here. So I-core is obtained as a ratio of B over RP. What is B? B is the Tafel constant, which is derived from anodic and cathodic constants, plugging in the values here. However, to derive the Tafel plot, we have to forward scan or polarize the system from OCP, that is open circuit potential, minus 100 millivolt to plus 100 millivolts at a scan rate of 1 millivolts per second. So you see two trajectories in this curve. So one is the anodic Tafel region, the upper one. You get beta A from there and beta C from here. So you plug in these values and get your I-core. So as per Rylam TC 154, any I-core above 1 mu amps per centimeter square would indicate that this system is corroding at a very high rate. So let's see what are our results. So for these are the trends for open circuit potential. So we note that CCs and VAs based alkali-activated concrete rebars, they show very high level of corrosion since the beginning of the experiment itself. But this is with respect to the OPC limits. So you see there is a drop in the beginning itself and then it sort of stabilizes in the same region. And however, the OPC, the black line, the OPC specimens, they sort of degrade over the time. The level of corrosion is high as per the code here as well. So in case of AACs, literature attributes this behavior to their unique pore solution chemistry and the lack of oxygen at the steel concrete interface in these systems, which is the attribute of their refined microstructure. So coming on to the RP trends, we see similar trends have been reported for linear polarization resistance. We see that there is a significant drop in the beginning and then it sort of stabilizes over the point of time when these results are obtained for 1 year. So, but interestingly, in case of OPC, if you see the drop is consistent over time, specifically after 4 months of testing. So there's some onset of corrosion activity in OPC for sure, but let's check whether it is there or not. So coming on to the thirdly, the corrosion current density results, we see highly apparent corrosion current densities for alkali-activated concretes, which show low to moderate level of corrosion in both CCs and VA based AACs. So that indicates that there is some sort of potential depassivation of embedded rebars for sure. And these systems, the AAC systems, are less immune to chloride-induced corrosion in particular. But to validate these test results, we had to retrieve the reinforcements at particular intervals. Here I am presenting the retrieved reinforcements at 1 year. So you see all the extracted reinforcements from AACs had no signs of active corrosion, whereas the OPC rebar over there has corroded to a certain extent. So this sort of makes us revisit the basic. So I-core is obtained from B over RP. So there is something to do with the B. So we have monitored this B over the time of the course of our testing from 0 to 360 days. So our B, the AAC's B varies from 10 to 35 in passive condition, whereas literature reports for B for OPC systems or Portland cement systems, it is 26 for an active corrosion system and 52 for a passive corrosion system. However, our values are 10 to 35, which are close to all the values reported for these low calcium based binders, whosoever has been retrospected till now for AACs against 52 of OPC. Hence, these OPC centric limits certainly won't work to predict corrosion activity in case of alkali-activated concrete. So the existing literature asks to make these thresholds more accommodative by 3 to 5 times. In my case, I have made them more flexible from 5 times. So you see now the corrosion activity would be suggested above 5 mu amps per centimeter square. So there would be high chances of corrosion by that time. So these are the recommended thresholds. So we see that they sort of work well in predicting the corrosion activity for our AAC systems. They are showing no low to negligible level of corrosion. However, with the time we will gain more data for active Tafel constant, and we will come up with more refined values or more refined these thresholds to certainly predict the corrosion activity with very accurate, with quite accuracy. So to summarize whatsoever I had in this presentation, all the tested alkali-activated concretes demonstrated significant resistance to chloride-induced corrosion, and this distinction is certainly due to the unique pore solution chemistry of these alkali-activated concretes. However, it was found that OPC specific limits won't fit in to verify the corrosion activity of alkaline-activated concrete. Thus, we need to redesign these thresholds to accommodate the actual condition which was confirmed by our extractions, and the revised limits, which may need certain revision further, will be they sort of are good in predicting negligible to minor corrosion in our AACs. Further, this work would be correlated with the pore solution chemistry and the bulk chloride diffusion response of alkali-activated concretes to check what is their impact on corrosion behavior. So I would like to thank Federal Highways for funding this project, Penn State and Purdue University for collaborating for this research, Camp Clarkson University, and Dr. Sulafa Pitampan for all the guidance. Thank you.